Hello everyone. Today's GAMS tutorial is related with the dollar condition. We will first introduce the syntax of the dollar condition. Then we will introduce how to use the dollar condition to restrict the domain over which the equations are defined. This is called conditional equations. We will also introduce how to use the dollar condition to assign values to parameters under some conditions, which is called conditional assignments. Finally, we will introduce how to use the dollar condition in the index operations under certain conditions, which is called conditional indexed operations. We first look at the syntax of the dollar condition. This is the syntax for the dollar condition. It starts with term and then dollar sign. After that is logical condition. The logical condition will be included in two brackets. The term can be a number like 2, like 0 in this example. The term can also be a symbol like A in this example. The term can also be an index symbol like BI in this example. The term can also be a complex expression like the summation expression in this example. The dollar operator may be read as under the condition that the following logical condition evaluates to true or is not equal to 0. That means if the logical condition is true, is not equal to 0, then we have this term. For instance, in this example, if b is greater than 1.5, then a is equal to 2. If b is less than or equal to 1.5, then a is equal to 0. This is because when b is greater than 1.5, this logical condition is true, and this logical condition is false. Then we have the term 2. So a is equal to 2. When b is less than or equal to 5, then this logical condition is true, and this logical condition is false. Then we have the term 0, so then a is equal to 0. For the second example, if b is greater than 1.5, then this condition is true. Then we have the term a is equal to 2. If b is less than or equal to 1.5, then this condition is false. Then we don't assign 2 to a. In this example, if the logical condition a times 2 minus 4 is true, then we have this constraint. Otherwise, this constraint will not be imposed. You can do the similar analysis for the remaining two examples. It is not too difficult. Besides the dollar operator in the dollar condition, the other importance is the logical condition. The logical conditions can be numerical expressions like 2 times a minus 4 in this example. The logical conditions can also be numerical relations like b is greater than 1.5 in this example. The numerical relations can be strictly less than or equal to, not equal to, greater than or equal to, strictly greater than. For different relations, we should use different operators. For instance, if x is strictly less than y, then we should write x less than y or we can write x LTY. If x is less than or equal to y, then we should write x less than or equal to y, or we can write x LEY. If x is equal to y, then we can use the equal sign, or we can use EQ. If x is not equal to y, then we can use not equal to sign, or we can write NE. If x is greater than or equal to y, then we can use the greater than or equal to sign, or we can write GE. If x is strictly greater than y, then we can use the strictly greater than sign, or we can write GT. All these relation operators are different from the equation type operator. When we define equations, we should not be confused with them. Okay, the logical conditions can also refer to set membership and the set functions. Let's see the set memberships first. In this example, we define set I. There are 5 elements, I1, I2, I3, I4, I5 in this set I. We also define the set J. J is a subset of I. It has 3 elements, I1, I2, and I3, and 2 parameters, Si and Ti, are declared. Si is also defined. Now we want to assign values to Ti when I is equal to I1, I2, and I3. We don't want to assign values to Ti when I is equal to I4 and I5. Then we can use this one to express. This is a conditional expression. In this expression, I should satisfy the condition Ji. That means this expression restricts the assignments to the members of the subset J. In other words, this assignment is made only if the set I is an element of the subset J. That means if I is equal to I1, then we have this assignment. If I is equal to I2, then we have this assignment. If I is equal to I3, then we have this assignment. But if I is equal to I4 or I5, then we don't have this assignment. That means we don't change the value of Ti when I is equal to I4 and I5. By default, the value for Ti when I is equal to I4 or I5 is equal to 0. The set functions can also be used in the logical conditions. There are 2 set functions, order and cut. The order function returns the relative position of an element in a set. The cut function returns the number of elements in a set. There are 2 examples to show you how to use these 2 functions in the logical conditions. In the first example, the logical condition is order I is equal to order J. That means if the relative position of an element in set I is equal to the relative position of an element in set J, then we have this constraint. Otherwise, this constraint will not be imposed. For instance, if I is equal to Beijing, then the relative position of the element Beijing is equal to 1, right? If J is equal to Rome, the relative position of this element is also equal to 1 inside J, so then this logical condition is satisfied, is true, then this constraint is imposed. If J is equal to Paris, the relative position of this element inside J is equal to 2. That means order I is not equal to order J when I is equal to Beijing and J is equal to Paris. Then this logical condition is not true. This constraint will not be imposed. In the second example, the logical condition is order I is equal to cut I. That means if the relative position of an element in set I is the last one in the set I, then this logical condition is true. Otherwise, this logical condition is false. For instance, if I is equal to Cairo, then the relative position of this element Cairo in set I is equal to 6, and the total number of elements in set I is also equal to 6. That means this logical condition is true, then this constraint will be imposed. If I is equal to Mumbai, then the relative position of this element is equal to 3. That means order I when I is equal to Mumbai is not equal to cut I. Then this logical condition is not true, then this constraint will not be imposed. We can also combine two or more logical conditions to form a complex logical condition. We can use logical operators to connect those different logical conditions. The logical operators can be not, not, can be and can be or, can be xor, can be imp, can be eqv. Usually we use not, and or logical operators. For example, if we have the logical condition like b is greater than 1.5 and c should be greater than 2, then we can write b is greater than 1.5 and use the and logical operator, and then c is greater than 2. Then we use this and logical operator to combine this logical condition and this logical condition. If both of them are true, then the entire logical condition is true. If one of them is not true, then the entire condition is not true. If we use the logical operator OR to connect X logical condition and Y logical condition, if at least one of these two logical conditions is true, then the entire logical condition is true. We can also use NOT operator. For instance, NOT X. If X is true, then NOT X is false. If X is false, then NOT X is true. If we want the entire logical condition to be true, then the logical condition X has to be false. These three operators are used frequently in logical conditions. For others, we seldom use them, so we don't introduce them here. You can learn them by yourself. In a complex logical condition, we may have different operations, such as arithmetical operations, numerical relational operations, and logical operations. We can use bracket to separate different operations. In order to calculate the value of the logical condition, we should know the precedence of each operation. In this table, we can see clearly the order of precedence for each operation. The first order of precedence is exponentiation operation. The second order of precedence is multiplication and division. Then is plus and minus. After that is addition and subtraction. Following that is numerical relational operations like strictly less than or equal to, equal, not equal, greater than or equal to, strictly greater than. All these relational operations have the same precedence. Following that is logical operations. In the logical operations, negation operation, not, is the first order of precedence. After that is AND operation. The last one is OR, XOR, IMP, and EQV operations. Based on the order of precedence, we can calculate the value of the logical condition. For instance, for this example, this is a logical condition. In this logical condition, we have different operations like arithmetical operation, like numerical relational operation, and logical operation. If A is equal to 2, B is equal to 5, then we can calculate the value of this logical condition based on the order of precedence of different operations. We first calculate the exponentiation operation. So this is equal to 4, and then greater than 2, and e times 3 plus 1 is greater than 1.5. Next, we calculate the multiplication and the division. E times 3 is equal to 15 plus 1 is greater than 1.5, and 4 greater than 2. Next, we calculate plus and minus. There is no minus and plus operation, so we don't need to calculate the plus and also minus operation. After that is addition and subtraction. This is an addition, so this is 16 greater than 1.5, and 4 greater than 2. Next is numerical relational operations. So this is 2, then this is also 2, and operator. Because both are true, then the logical operator AND will return the value of 1. So then the logical condition is true. That means this constraint will be imposed. Finally, I also want to mention, in the logical condition, variables should not be included. This is because we should know the value of the logical condition before optimization. For this example, if B and C are variables, then GAMS will provide you some error message. This is very important. Next, we will use logical condition to restrict the domain over which the equations are defined.